In today's lecture, we are going to discuss about the performance equation for an ideal plug flow reactor. As all we know that plug flow is an ideal flow pattern existing inside the reactor, in which the reaction takes place only in the axial direction, but not in the radial direction. A plug flow reactor resembles like a cylinder kept horizontally, as we can see from the diagram. And also for this equation, for this reactor, the important design parameter is reactor volume. So we have to use the mole balance concept to find the design equation or performance equation for a ideal plug flow reactor. So plug flow is an ideal flow condition, like a mixed flow. So here we can see that through the reactant called as A is entering. It is having initial concentration called as A0, and the molar feed rate of the reactant is Fi0. The initial concentration is 0, and this V0 is the inlet volumetric flow rate of the reactant entering into the reactor. And these things are the final properties of the exiting stream. As we can see here that as the reactant is moving inside the reactor, the conversion is changing. Conversion is increasing gradually, like from entrance to the exit. See, now based on this elemental volume, we can see there is one small portion inside the reactor that is taken as the elemental volume, a small cylinder. So based on small cylinder and based on the number of moles entering into small cylinder, leaving from the small cylinder, we can write the expression for that the mole balance equation we can write, from which we can able to form the design equation or performance equation. So in a plug flow reactor, as you can see here that the composition of the fluid varies from point to point along the flow path. That means that as the molecule is moving from entrance to exit, the reaction will be taking place. So along the length of the reactor, the concentration will be changing in a plug flow reactor. And this the general mole balance equation for a system in which reaction is taking place. So input is equal to output plus disappearance by reaction and accumulation. So obviously accumulation term is 0 because the system is at steady state. So the input modes of A, as we have seen in the previous the PPT or slide, the input modes of A is Fa, and the output modes of A is Fa plus BFA. It is based on the elemental volume. Both these terms are based on elemental volume, and also the number of moles disappearing by reaction inside the elemental volume is minus RA into dV. Okay, the minus RA is nothing but the rate of reaction. The dV is nothing but the small volume, like elemental volume capacity. Okay, the elemental volume capacity. Now introducing the terms in the equation, the mole balance equation. So we get Fa. This is the input term, output term. This is the rate of disappearance term. And then expanding this BFA term inside the elemental volume, we can write it as BFA is equal to differential of, as we know that this Fa can be replaced with Fa0 into 1 minus Xa, and after differentiation we get an equation like BFA can be replaced with minus Fa0 into dxa. And then this BFA term is replaced here in the previous equation, and then further simplification will give an equation in this form. So now this is applicable only for the elemental volume, but we would like to, this dV represent the volume of the small cylinder inside the large reactor. Now we want to extend this equation for the entire reactor setup. So for that we have to differentiate, we have to integrate the equation for the entire reactor volume. So now after rearrangement of this term, and then we have to take the volume to one side, conversion to the other side, because they are the variables. Then the integration should be applied for the resulting equation what we get there. So after integration, as you can see that volume varies from 0 to V, conversion varies from 0 to XAF. So upon integration, the final equation what we get is excuse me, it's not going properly. When you stop it exactly. Okay, so after integration, so what we get is like V by Fa naught is equal to integration of dxa by minus Ra. Already we know that we have a relationship between the space time and the reactor volume. That the relationship is also like put in here, and then we could able to get the final design equation for the ideal control reactor. So from this equation we can calculate what is the reactor volume or space time also we can able to calculate. So thanks for listening to the lecture.